Day 134, Honors Physics, Electrostatics. Homework problem number 42. This is not a capacitor problem. You can kind of see that. We have two little charged spheres. We don't know if they're both positive or both negative, but we do know they both have a like charge because they're repelling. It's kind of like when I had the two negative balloons hanging from those two threads in class. They repelled each other. They didn't hang straight down. The key on this diagram, on this problem, is going to be a free body force diagram. I'm going to look at the two charges separately, but then I'll just focus on one of them. But let's take the 6 grams on the right. It has a string pulling up and to the right. Let me get that a little bit closer to the actual angle. So that angle is up and to the right. That's the tension in this string. I can label it up in the diagram as well. There's a tension in that string right there, pulling up and to the right. It's going to have a component to the right and a component up. And then also on that charge, well, the same thing is true. Let's just try the other one. The 6 grams on the other side, it's going to have a tension this way. It's going to be equal to that one. There's a lot of symmetry here. So they're both going to have strings pulling on them up. The one on the left is up and to the right. The one on the right is up and to the left. The components are. You'll see that in a minute. All right. Also, we have the force of gravity pulling down on these objects. So I'm going to call it F sub g. That's the weight of the object, which we'll calculate in a second. So they're both being pulled down by gravity, straight down. But also, they're repelling each other. And the way we've shown that before is with two equal and opposite arrows. Now we have two forces, and we'll use Coulomb's law here in a minute. But they're repelling each other. We call it F sub E and F sub E, which will be calculated by, I'll go up to the upper right here, but even though it's going to be the last step I do in a problem, F sub E equals K Q1 Q2 over their separation distance squared, R squared. That's the electrical force of repulsion or attraction if they're a positive and negative, which they're not here, they're repelling. So I've shown that with two outward arrows there on the diagram. So I have my proper free body force diagram for each of the two charges. But I really only need to focus on one, because once I have the answer for one of them, let's say let's take the right one here, it's really going to be the same answer for the other one. And the key is whenever you have these free body diagrams and you have one force at an angle, what you want to find are the components. So I'm going to do that in a separate diagram right now. This T right here, okay, it has a component to the left, T sub x, and it has a component up. Now I can draw the upward component here, or I can draw it here. Take your pick. It's an upward component. I'll draw it over here right now. So it has an upward component right there. That's T sub y, and T is the hypotenuse. All right, so it has those two components. But the bottom line is I need to know the angles, because I want to figure out those components relative to T. So let's figure out the angle. If we go to the diagram, at the very top up here, actually I'll redraw the diagram in blue. I'll trace it in blue and then I'll redraw it in blue. This diagram right here is the triangle, the geometry of the triangle. I'll draw that over here, way over to the right. So here's the geometry of the triangle. And I want to figure out these base angles of the isosceles triangle. I'm going to drop an altitude straight down, and it splits the base into a 10 and 10, because the base is 20, this is 10 and 10, and the hypotenuse here, the isosceles legs, the two equal legs, are 30 and 30. So bottom line is I want to get this angle over here. I'm going to call it theta, far on the right over, way over here on the right, I'm going to get theta. And if I use cosine of theta, that will give me, for this right half of that triangle, if I look at this triangle right here, this triangle, half of the big isosceles triangle, but I'm looking at a right triangle now, the cosine of theta is the adjacent leg 10 over 30. So yeah, that's 10 over 30. So you do inverse cosine, you get theta, I believe, is 70.5 degrees. So that's important because it goes to the component diagram way down here on the left. This diagram right here, I have, that matches up to this angle right here. That angle right there is 70.5, which means this angle right here is 19.5 degrees. So you can look at either one of those, or you can actually complete the rectangle. If I just put a dashed line in here, trying to complete the rectangle, because I want to find those two components, T sub x and T sub y. Eventually, I really can't do it quite yet. I'm just going to label this theta. This black theta right here is the same as the 70.5. I'm going to be using that eventually. But let me just write that down. Theta is the same as the geometry that I showed in the upper right here. here is 70.5 degrees. All right, but what I want to do, it'd be nice if I could get those actual components right now. But I'll come back to that one. Because that's all I know is the angle. I don't know anything else. So I can't do anything with that right now. Excuse me. So what I'm going to do is take my diagram. The key to these free body diagrams is to get to the simplified component diagram. So this is the key diagram I want now. I'm going to transpose that diagram right here into the component diagram. So this is the dot, that 6 gram dot mass. It has F sub E this way. It has F sub G this way, but I know, actually I can figure that one out, because I know the weight of this thing. I can figure out F sub G, because weight, or F sub G, equals mass times gravity. So F sub G here, that actual downward force, is the mass, 0.006 kilograms times 9.81. So if I do that, I get the force of gravity here is 0.0589 newtons. 0.0589 newtons. That's this force right here. That's going to be key. 0.0589. I could have said 58.9 millinewtons. All right, so that's that downward force of gravity, this force right here. The weight of the little particles doesn't weigh a whole lot. So if I complete the diagram now, what I want to do is put the components of T. I don't want T anymore. I want the components of T. So T is going to have a T sub X, and it's going to have a T sub Y. T sub Y. I drew that a little bit too long, because T sub Y should really be equal to 0.0589 newtons. It's got to have the same size. This is balanced out. So I'm going to erase that and make it a little shorter. Yeah, so that's upward T sub Y is the same strength as the 0.589. So I know that this equals that. Okay, or in other words, this is that. So T sub Y is 0.0589 newtons. Because this is an equilibrium, the up force has to equal the down force. It's not accelerating. Oh, now that I know that T sub Y is equal to that, I can figure out T and T sub X, because I know that, let's call this alpha over here. Doesn't really matter which angle you use, but alpha is going to be 19.5 degrees. I could have used the 70.5. But if I use the cosine of alpha, the cosine of the 19.5, cosine of 19.5, and if I look at this triangle right here, that's going to be T sub Y over T. In other words, that's going to be 0.0589 over T. I can figure out T. And once I have T, I can use Pythagorean theorem or sines or cosines to figure out T sub X. So I'm going to go do that now. You don't need to show me all this, so you've showed me enough so far. I'm going to go do that on my calculator. So right now I'm going to get T, and then using sines and cosines or Pythagorean theorem, I'm going to get T sub X and come back to you. So I've done the math here. T is this. I really didn't even need T. T is this. What I really want to have is T sub X. Because T sub X, now that I know T sub X, all right, I know T sub X. I use sines and cosines on this component diagram. Or actually, I used the Pythagorean theorem. So I know T sub X, and this is equal. This whole thing is an equilibrium. So the key now is this diagram, this free body force diagram. This force has to equal that force. In other words, I know now the electrical force is the same as T sub X. So I know this electrical force is also 0.0209 newtons. And that is going to go in this equation right here. Let's go way up there. I'll use black now. So this will be 0.0209 equals K, which is 9 times 10 to the 9th. That's a 9 there. Let's try to do better with that. Times Q times Q. Well, the two Q's are the same, so I'm just going to call that Q squared, which is going to give me the one variable that I need. And I know the distance apart that those two charges are. It's 0.20 meters squared. So now that expression will give me the final answer, or that equation. That'll give me Q. Each Q is the same. So I'm going to go to my calculator and do that. So I do that, and I ended up with 3.05 times 10 to the negative 7th coulombs. The answer sheet says 3.04. Actually, it says 0.304 times 10 to the negative 6th, which is the same answer, coulombs. 3.05 times 10 to the negative 7th coulombs is the same as 0.304 times 10 to the negative 6 coulombs. So there we go. That problem's pretty involved. So that's the charge in each of those little spheres hanging from those strings. And let's say they're positive. Doesn't really matter. They could be both negative.